In this video, I'm going to teach you how to read the ANOVA table used in SPSS regression. As a reminder, the grades are the dependent variable, and absences and SAT score are the independent variables. In the first video, I discussed how to build the actual regression equation. In the second video, I outlined in some detail how to read the coefficient table. This is the third video, and I'll explain the ANOVA table, how to read the ANOVA table in a lot of detail, and I'll walk you through that step by step, what all these pieces, all those values mean. And in the fourth video, I'll discuss the model summary. So in this video, I'll show you how all these numbers are derived, and I'll also show you a representation of these numbers visually too. Let me just move that table up a little bit, and I will begin. The first column I'm going to discuss is sum of squares and how these numbers are actually calculated. And up first, I'll talk about total sum of squares. The way this number is derived is I take grades, or my dependent value, and I calculate the mean. In this case, it's 76. And I'll make another column of mean grades. And what I'm going to do is I'm going to take the difference between the grades and the mean grades, and then I'm going to square it. I take 82, the grades, minus the mean grades, which is 76. I'm going to square this. And let me show you. So 82 minus 76 is 6. So 6 squared is 36. I'll just do this one more time. So I take 98 minus 76. I square it, which is 22 squared, which is 484. I'm rounding also. And then I'm going to add up all these values. I'm going to sum them all up. And that's going to be my total sum of squares. So let me just fill in the rest of the numbers. And again, I'm rounding. Don't worry about that. And I add all these up, or sum them up, and it equals to, you got it, 2,262. And that is my total sum of squares. Let me pop over to a graph of this so I can show you visually what I'm doing. So these dots are my actual values, my actual grades. And that's my independent variable, actual grades. And I'll take the mean of the actual grades, which was 76 if you remember. And in essence, what I'm interested in is the distance between the actual value and the mean. And that's my total sum of squares. In your textbook, and probably your professor uses notation like this, yi and y bar, and they square it. I think it's kind of confusing, but again, it's grades minus the mean squared, and the notation looks like the sum of yi minus y bar squared. And now I'm going to talk about the sum of squares for the regression model, or the actual equation. And in the first video, I derived this equation and calculated estimated grades. The way I calculated estimated grades is just by plugging in the actual values for absences and SAT scores. Now I take the estimated grades minus the mean, which is 78 minus 76, and I square that. So I add in a column, and 78 minus 76 is 2, so I have 2 squared, which is 4. Again, I'm rounding, it's okay. Just like before, I'm going to do this for each individual value, and then I'm going to add all that up, and I'm going to sum it. So let me do that now. Let me just put in all the values. And again, I'm rounding. Don't worry about it. It's all good. And this all adds up to 2105.435. So I sum it up, 2105.435, and that is my regression sum of squares. That's for my model itself. Now remember, total sum of squares, which I just did, is my actual value compared to my mean. So let me draw the mean line in. So it's the actual values minus the mean, the distance between those two. And I square it and I do some other things, but that's in essence what it is. So now, I'm going to do regression sum of squares. So I draw on my regression line. The brown dots are the estimated values. So regression sum of squares is the estimate value minus the mean. And again, I'll square that, but that's in essence what we're doing. We're looking at the distance between the estimate and the mean. And again, your professor is probably using some type of notation, and your book does. And the notation is y hat for estimated grades minus y bar for the mean. And so you'll see in your book, and your professor probably uses this notation right there, the sum of y hat minus y bar. Something like that. Now the last sum of squares is the residual. So now I'm going to take my grades and my estimated grades and compare those. Let me show you graphically first. So residual sum of squares, residual errors. I'm going to take the actual, and let me draw my regression line. And again, the brown dots are my estimated values. And I'm going to look at the distance between those two. So I'm going to take the distance between my actual and my estimated. Now I'm going to take my grades and the difference between grades and estimated grades. Remember, estimated grades are just my actual values plugged into this equation. And that would give me 78 for student 1. That's where that 78 comes from. And now I'm going to take the difference. Now, hang on here for a second. It doesn't make a difference if I take grades minus estimated grades or estimated grades minus grades, because I'm going to square it. 82 minus 78 is 4, and 4 squared is 16. And I'm going to repeat this just like I did before for each of these grades minus estimated grades. I'm going to sum it all up. And sometimes you'll see this recalled or referenced as errors. And again, any of these things I'm doing where I'm squaring it, the order does not make a difference. So don't get hung up on that when you're doing your problems, and also tell your professor, hey, the order doesn't make a difference because I'm squaring it. Anyway, so the sum, I just add all these up, equals 156.565. And that's the residual sum of squares, or the errors of the sum of squares. You'll see it referenced as that. Now for a little notation, I think I got notation, yeah. I take grades, which is yi minus y hat, I, square it all up. By the way, that little I, all that means is do this for every single value or every single observation or for all the students. And the sum of yi minus yi hat squared is the notation that you'll see often in your books and your professor uses. And it turns out that regression plus the residuals is equal to the total. So regression model, sum of squares, plus residual sum of squares is equal to the total sum of squares. Let me show you. 2,105 plus 156 is equal to 2,262. Again, I'm rounding, that's okay. The DF column is degrees of freedom. The degrees of freedom for the model I built, the regression model, is built upon the regressors, or the three variables, which are constant, the absences, and SAT scores. Those are the three things I'm estimating. So I take 3 minus 1, which is equal to 2. And I'll put the 2 up there. Degrees of freedom is a difficult concept, and I discussed that on another video on my channel. Now if I take my sum of squares divided by the degrees of freedom, which is 2, this is equal to 1052, which is the mean square. The degrees of freedom for the residual, or for the errors, is based upon the sample size. How big is my sample size? Which is 10. And my regressors, which are the three variables I'm estimating, which is 3. So I have 10 minus 3, which is 7 last time I checked. Something to consider is, as my sample size got large, my degrees of freedom would also become large. Keep that in mind. Now I take my residuals and divide by degrees of freedom, which is 7. And this is equal to 22.366, and that's my mean square. And it turns out that if I take these 2 degrees of freedom, added them together, that gives me my total degrees of freedom. So now I take my mean square of my regression divided by the mean square of the residual, that ratio, and this is equal to my F-score, which is 47.067. There is a 0.000 chance I'm getting this by some random chance, and that significance, that sig means significance, the same as p-value. The ANOVA result is written as F for Fisher, but F parentheses 2, which is the regression degrees of freedom, comma, the residual degrees of freedom, and this is equal to 47.067. You will often see the 2 and 7 labeled as such, the degrees of freedom of the numerator and degrees of freedom of the denominator. I have an entire playlist on ANOVA I'd encourage you to watch as well to help you understand this concept. Now I'll draw in the distribution. The F distribution looks something like this. Kind of a goofy looking bell curve. Plot my 47.067, and the probability that results are by some random chance is that red area, and that 47.067 actually means it's off the chart. Just keep going. There you go. And this is actually a good result, so we want that when we do hypothesis testing. So hopefully you kind of grasp some of the ideas of how this ANOVA table is built and developed. And up next is the model summary table, and I'll walk you through that step by step. As always, don't forget to share the knowledge, share the love, Facebook, Google+, Twitter. Questions, comments, and suggestions below. Like us, please. And do subscribe because I'm always posting new videos about statistics.